So everyone's checked in, right? Welcome to our second paper reading group of the year. Before we get started on the meat of the paper reading group today, we're just gonna, take you through. Wait, is this anyone's first time at our paper reading group? Welcome. Okay, so just wanted to introduce ourselves a little bit. We're the Data Science Statistics Society. And we focus on all the cool stuff that's happening in the industry with regards to data science, AI, machine learning, all that cool jazz, and we bring it back to school. We do a lot of workshops, a lot of events happen. So this month, I think for the past couple of weeks, in the next 3 weeks, every Wednesday we have an event happening. So next week is the start of our Intro to Data Science workshops, if you guys are interested. But yeah, that's just a little bit about us. So what is a paper reading group? Basically, we come together and we look at an academic paper together, and we have an academic representative, such as Malhar, take you through it, help break it down for you into something that's digestible, because let me tell you, these papers are hard to read. Not for Malhar, maybe, but for a layman such as me, it's very hard. And then hopefully, with him helping us read the paper, at the end we can have a little discussion, a little commentary about, what the hell happened in the paper. But yeah, did I miss anything, Malhar?
No, that's about right.
That's about right. Okay, I'm gonna pass it on to Malhar now. Slowly, and let him take it away.
All right. So briefly, I asked you guys whether you guys watched the 3 Blue 1 Brown video. For those of you that just received the email, did you get a chance to look over it? Some parts. Okay, that's fine. We're gonna briefly go over some concepts. So before we do a quick recap of the 3 Blue 1 Brown videos, let's talk about what this paper is. So this paper is one of the most cited papers in machine learning. It is a 2014 paper done by researchers at U of T. It's called Dropout, a simple way to prevent neural networks from overfitting. There's a lot of terms here that might be confusing. What does overfitting mean? What's dropout? We'll talk all about that in detail. A neat little thing about this. Who here knows Geoffrey Hinton? Can you tell me who he is?
He's like the godfather of AI.
That's correct.
I think he was the one who started neural networks and research on them.
He was on this paper. He helped make this paper. Okay, so before we dive into how to improve basic neural networks, what we're going to do is we're going to briefly do a recap of what a neural network is and how we can use it. So in the 3 Blue 1 Brown video, and I'm going to stick with that example, what we were trying to do, the goal or the task at hand was to recognize digits, handwritten digits, right? And there was a large database of, an image of a hand-drawn digit and its correct label. And the task was to use neural networks to make it learn how to recognize each digit, right? With a high accuracy, of course. So in that case, the image was a 28 by 28 image, right? Which gives you a total of 784 pixels. And all of these 784 were basically inputs to the neural network, okay? So you have pixel 1, you have pixel 2, so on and so forth. You have pixel 784. Now, a neural network is basically a big function. How does it look like? Okay, it mainly has 3 sections, right? It has the input section, which we just talked about. It also has, of course, the output section. And in our case, because we want to recognize digits, and there are 10 digits, our output would just be 10 of these quote-unquote units, and whatever the neural network, does compute and whatever, at the end, each unit will have a value between 0 and 1. That value for any of these units is called its activation. Okay? And basically, when you have these 10 outputs, the highest output is essentially what the neural network is claiming that, that input is, right? So if there's a 9, then let's say this is for digit 0, this is for digit 1, 2, so on and so forth. This is for digit 9. If it's a good neural network, it will most likely have a high activation or output value for this unit, the one that corresponds to 9, and it will have ideally low outputs or low activations for the rest. Okay, but how does this happen? Well, there's a third component. This is called the hidden layer or hidden layers. And they're essentially just, columns of these units. These individual units, I want you to sort of look at them analogous to how neurons work in the brain, right? Neurons in the brain, a whole bunch of them are connected differently, and when a signal passes through one, depending on how the synapses connect, the signal gets forwarded, it gets amplified, or it gets de-amplified. That's essentially what's happening here. You have a bunch of these hidden layers, and of course the number of units in each of these layers is not necessarily the same, but the one defining characteristic is that you have these sort of edges that go from one layer to the next, and each unit in this layer will be connected to every unit in the next. And this edge will have some weight associated with it. And there's some very simple linear combination math that happens here to compute the value of this. So since every unit has an outgoing edge to every unit in the next layer, you can also see that every unit here has incoming edges from every unit in the previous layer, right? So you have the incoming edge from unit 1, you have the incoming edge from unit 2, you have the incoming edge from unit 784 from the input layer. And to calculate the quote-unquote activation of this unit, all you have to do is you have to take the activation of the previous unit, multiply by its weights, and sum all of those up, right? So if the activation for this is A1, and for the second unit it's A2, and so on and so forth, the value here would basically be A1 times whatever weight the edge has, plus A2 times weight number 2, so on and so forth. You get this sort of sum. Now, of course, we don't want the sum to blow up. We want to scale it down. So there's a shrinking function that's called the activation function. It just shrinks down the numbers to a range between 0 and 1, right? We're not going to focus a lot on this, but this is the general gist of things, right? So, of course, this, as you have learned or you might learn, is a linear combination. There's no constant term. Every term here depends on the previous activation or the activation of some previous unit and the weights. Additionally, you also usually have a constant which is called the bias. Again, this is just a quick recap. We're not going to focus too much on this. Overall, what this neural network does is you give it an image, it breaks it into all of these pixels, and then it computes it, and ideally, let's say the image was a 5, then you should see the output for 5 to be high, and you want the output for everything else to be low. If that's not the case, which it won't be at the very start because the weights are just random, we have to tell it to fix itself, right? And that's how it learns. We fix it by tweaking the weights, okay? So that's a little bit about how neural networks work. In essence, you have a large set of images, which is your training sets, and you do this sort of training for every image in the sets, and after, let's say, 100,000 iterations, it should have learned to identify, different things. After you have this, of course, you can't just, say, okay, this is perfect, because what if it was just working on the training set? What if it sort of figured it out exactly for the training set, but if I give it, a new handwritten image, it's not able to figure it out, right? So we have a separate sort of testing thing, and we test it on the test data set, but we don't train it on the test data set, yada, yada, yada. Okay, cool. That should be a good enough introduction. So let's get into this paper. What is overfitting and what is dropout? Okay, so deep neural networks are nothing but neural networks that have many hidden layers, right? The number of hidden layers required before it's called deep, that's subject to debate, but usually people consider anything more than 5 or 7 layers to be a deep neural network. Such neural networks can learn very, complex relationships between, let's say pixel 2 and pixel 40, right? Very complex. In fact, so complex that maybe it's learning things that it's not supposed to. It's because of how our training set is limited. Maybe it was just written by one person, and that one person always writes their 7 with a dash, right? But that's not the only way to write a 7, is it? But it might just learn that I need this dash for the 7, right? So it's learning very complex relationships, and this leads to overfitting. By overfitting, all I'm saying is that sample noise, which is basically, the sample size or the training set being limited, and having, I don't want to say unwanted, but coincidental correlations between input. If it learns those, and those relationships don't actually exist in general, then when I try to test it or just apply it in a real world scenario, it's going to try and look for those relationships where it's not necessary that those exist, right? So it's going to work amazing on the training sets, but when it tries to look for those correlations on the test set or in general, it's not going to perform as well. Okay? So to fix this, there have been a bunch of modifications, improvements. These are called regularization techniques. Regularization is essentially desensitization in the sense that you make sure that no small subset of the training set ends up, impacting the weights too much, right? The only thing determining how good this neural network is at the end of the day is the weights and the shrinking function, right? But more so the weights. And so we don't want just like a small subset of the training data to end up heavily impacting these weights. So we sort of try and desensitize it. And if you take C11, you'll learn some of these. You'll learn L1, L2 regularization. But these are some ways to prevent overfitting, right? Ideally, what you want to do is you want to figure out every possible scenario, every possible combination of all the weights, and then just test it on all the possible combinations and pick the best one, right? That would be the absolute best we can do. What's the problem here? The problem here is that that's too much work. That's too much computation, especially for deep neural networks, right? If you have n units, then you have the order of n squared weights. And imagine having to tweak them. And these tweaks aren't, chunked. It's not like 0.1, 0.2, 0.3. You can tweak them as fine as you like. So your weight space, or the set of all possible configurations, is too much to actually just train and figure out. Okay? You also might run out of data. you might run out of meaningfully distinct data, and you might be running the same training data on different, weight parameters. That's also problematic. Okay? Great. So in comes Dropout. What is Dropout? It's an architecturally efficient technique for approximating the model combination, right? So, like I said, of course, we can't really figure out all possible combinations of weights. Not only that, those weight tweaks are for a specific network architecture. When I say a specific network architecture, I mean I'm fixing the number of layers and I'm fixing the number of units in each layer. But ideally, not only do you want to figure out all combinations of weights, you also want to test it on different sort of architectures. What if instead of 2 layers I have 3? What if the middle layer has twice the nodes than it has right now? Right? There's a lot of combinations. So that's what you're trying to do. And Dropout does that efficiently. How does it do that? Okay. Before we go to how does it do that, let's see what the outcome is. The outcome, as expected, is our goal. That is that it reduces overfitting. What's interesting is that it does so better than every other regularization technique. At least, of course, up until 2014, I guess. The idea, the very basic idea, is when we're training, instead of just looking at all the units, we're going to randomly drop them. We're just going to randomly drop a few. Okay? Or you could view it the other way around, where P is the probability that you keep a specific neuron or unit, right? So for example, if the probability of retainment for this was 0.5, what I'm essentially saying is if I train it 100,000 times, then on average, 50,000 times, I will actually remove it before I train it. Okay? They sort of figured out that keeping hidden units sort of like a 50-50 and keeping the inputs retainment at a 0.8 seems to work well. Of course, you want a high retainment on your input, because if your retainment on the input is something like 0.5, it essentially means you're only looking at half the image on average for every iteration, right? So we don't want that. Okay? Great. So I mentioned this before. If there are n units, the number of weights and biases is still just quadratic, right? Because you just have edges from one layer to the next. But the different possible network architectures that are constructed are exponential. They're 2 to the power n. How are they 2 to the power n? Well, for any iteration, I can either have a particular unit or not. So that's 2 options. And then you have those 2 options for every unit. And there's n units, so you have 2 to the power n, different possible network architectures that are created, right? So training with this technique is sort of similar to training 2 to the power n subnetworks, right, with different architectures, very sparsely. We're training them very sparsely, but notice that they share basically the same weights, right? So if any subnetwork where these 2 edges exist, they have the same weight, right? In all of the, 2 to the power n over 4 subnetworks there are. Okay, so that's the idea. The very small modification before we, while we're training, just make sure we just randomly drop a few units. By dropping a few units, I kind of mean just essentially setting its output to 0, right? Like, don't worry about its input and just output 0. It's turned off, quote unquote. Okay, so once you've done all this training, during testing, you have to you keep all the units, you don't randomly drop them. But here's the problem. Like I mentioned, the input to a particular neuron is sort of a linear combination, right? Now, if on average, my P was, let's say, 0.5, if on average I'm dropping half the units, I'm also dropping half the units from the previous layer specifically. So during training, on average, you only see 2 out of 4, for example, right? But during testing, I see all 4. So now when I do the weighted sum, this weighted sum on average will be twice the weighted sum during training. So just to account for that, we just multiply the weighted sum with P, right? In our case, it was 0.5. So it's just to balance the quote-unquote lack of units being dropped, right? So what ends up happening is that the output on the test set becomes equivalent to the expected output on the training set, right? You'll learn more about expected values and stuff in B52 and A67 in the later part. But essentially, it's, at the end of the day, we wanted to take like a model average of all the possible networks. And this is an efficient way of doing that. Of course, it's not the exact way of doing it, but it's computationally efficient, right? It approximates it. Okay. Great. So this is what it looks like, right? On the left side, you have a normal neural network. Look at how, that's a lot of weights, right? But after you randomly drop some, you're just like disconnecting them from the network. So in some particular iteration, this is what the training or the neural network is being trained on, right? In the next iteration, it's not necessary that you'll be training on the same network. Maybe you're dropping some other neurons and maybe you're keeping these two, right? Okay. And this is basically talking about how we're accounting for every unit being present. So during training, of course, this particular unit is only present with some probability P. And only with that probability P does it actually provide output, of course, times the weight to the next unit. But at testing time, this unit is always present. So it's always giving this PW output to the next unit that it's connected to. So this is always present, so it's always giving the W to the next layer. But to account for the expected training, because we trained it on the expected sort of subnetwork, we multiply it with P, right? So this is what allows us to, maintain, I guess, in a sense, the characteristic of the training model, right? So who came up with this and why, and what was the idea? How did this group come up with this idea? And what they claim is they had 2 motivations. The first one is the role of sex in evolution, right? So they sat down together and they thought, why do advanced organisms reproduce sexually, where the child takes half the genes from one parent and half from the other, as opposed to asexual reproduction, where the child just takes the parent's gene sets and modifies it slightly, right? Asexual reproduction ends up showing something called co-adaptation. It just means that the entire gene set is very, very specialized. So because the child inherits the entire gene set of the parents, what ends up happening is over time, this gene set starts to learn to work with itself, right? The mutations become very, very specialized. What ends up happening is this gene set becomes very, very codependent, right? Every single gene might end up being doing a very specific job, and it might be dependent on other genes that also are doing very specific jobs, right? This might be problematic, and we'll look at it, why this is problematic later. But the issue with co-adaptation is these groups of items, these genes, modified together to work well as a whole, right? but individually, they might actually not be able to do a lot. Or if you were to take a small subset, any random subset of this gene, it might not be able to handle everything, right? Because some of these genes might require some special genes that weren't in the subset. So one reason they give as to why advanced organisms reproduce sexually is that natural selection might prefer mixability over just individual fitness. By mixability, I just mean the ability to just take a random half from one parent, a random half from the other, combine them together for the child, and still have a well-working, functioning organism, right? This makes them more robust, right? You can take any half from someone, another half from someone else, and most likely the genes will still work well together, right? What this also does is it reduces codependency in the gene pool, right? Why? Because the offspring might not get the entire set of required genes, might just get a random half, right? So you can't depend on this gene and this gene both being present in the offspring, right? So it learns to work in smaller groups. It learns to work with a smaller set. Okay? Similarly, Dropout ends up training the hidden units to not rely or depend on other units, right? Why? Because in the next iterations, the unit that it depended on might not just exist. We might have just crossed it out, right? So this particular unit cannot heavily depend on this one because there's a 50% chance, or during half the training, it's not even there, right? The second idea behind this was the idea of conspiracies. Who believes the moon landing was fake? No? Just me? Okay. Right. But the idea here is that more conspiracies with fewer participants are more likely to be successful or effective than a single conspiracy with a lot of participants, right? For example, let's say, how easy is it for a group of 5 people to prank one person versus a group of 50 people to prank one person? The difference is, in a group of 5 people, you just need 5 people to do their part. In a group of 50 people, you need all 50 people to do their part and never mess up, right? That is much more unlikely, right? It's the same thing with the conspiracy with the moon landing being faked, right? How likely is it that everybody who was in on it has still kept their mouth sealed after all these years, right? It's pretty unlikely. Versus how likely is it that I'm stealing my friend's, cookies? It's plausible, right? So, of course, under testing conditions, under controlled environments, if you give all 50 people, all of their little jobs, you open the door, you pull out the gun, you hold the hostage, you take the money from the bank, it will work well. But in dynamic situations, it might just completely just crash and burn, right? So under dynamic situations or dynamic environments, the larger the group, the more likely it is for some of them to not do their part and the conspiracy as a whole fails, right? That's another sort of inspiration that they drew upon. Complex co-adaptations, complex codependencies, hey, gene number 1, I'm opening the door. Gene number 2, you're pulling the gun out. Work well in controlled environments. They work well when they're huddled around the blueprint of the bank. But when time comes, situations change, right? Maybe the escape driver is late because traffic or some accident happened or whatever. All of that happens. So complex co-adaptations work well on training sets, but are going to fail when applied in real-world situations or on the test data, as opposed to smaller codependencies that are just learning smaller, simpler things, right? Okay, great. So in essence, what this model is doing is it's just increasing the number of steps by 1. Okay? So this is a standard network. Like I mentioned, every unit is connected to has an incoming edge from every previous unit, right? And there's a bunch of weights, and there's also this +1 is the bias term. Like I mentioned, don't worry about it too much. But you get all these weights, and you get the output, which is y3 and y2 and y1, and you compute the linear sum, the linear combination, and then you apply the f, which is the shrinking function, to get your output. The only thing different here is before you pass in the output and compute this linear combination, you flip a coin. You flip a coin with probability p of landing heads. And when it lands heads, then you let it go through. But if it lands tails, it essentially means you dropped that neuron, right? So if it lands tails, you set it to 0, right? So that's it. That's the only extra step we're doing, this coin flip. Okay. Of course, a quick note here. This works well for the forward part of learning, but the backward part, which is actually tweaking the weights to make it work better, some thought had to be put into that because not all the units are always present. So it's not just, just do, import from Python, import backpropagation and just apply it. They had to tweak it a little bit. We're not going to delve too much into that. Okay, great. So what did they actually find? They found that doing the dropout or applying the dropout technique achieves state-of-the-art performance on benchmark data sets from many, many different domains: computer vision, gene splicing, image detection, speech recognition, right? We're not going to look at all of them, but we are going to look at a few of them that are a little bit more descriptive, right? So we'll be looking at MNIST and ImageNet, but I'll briefly talk about the others as well. So MNIST is the 3 blue, 1 brown data set of handwritten images, handwritten digits, right? That's what this example is based upon. That's what the video is on, right? It's a standard toy data set of handwritten digits. TIMIT is for speech, right? It's for clean speech recognition. CIFAR 10 and CIFAR 100 are just images, tiny images. SVHN stands for Street View House Numbers. So those Google cars going around on Google Maps, when they scan it, they also get the house numbers. So these are just like a set of cropped house numbers, right? Kind of similar to digit recognition, but now house numbers can have many digits. The Google camera might have taken it at an angle. There are different sizes, different colors, all of that, right? ImageNet, similar to CIFAR, is a collection of natural images, right? So nothing from like Wombo or Dream AI. They're just like regular camera, took a photo, added to the data set, right? Routers is a collection of articles, and alternative splicing is a data set of RNA features, right? So of course, we're going to use MNIST and ImageNet because we have images and outputs that we can find. So let's look at MNIST. So don't worry too much about all this mumbo jumbo. This is basically talking about the activation function. Different activation functions do different things. The network architecture, basically how many layers it has, how many units you have in each layer. What we want to see here is that a general neural network has an error of 1.6%, right? But when you do dropouts, it goes down to 1.35. And when you apply even additional, other improvements to this, it goes down all the way to 0.94. And then this over here, this is talking about deep belief networks and deep Boltzmann machines. Those are a little bit more complicated. But it essentially allows you to pre-train the network so that you don't start the weights randomly, but you have like a general idea of things and the weights. And then after you have a general idea of the weights, you just apply dropout again to fine tune it. And that brings you down to under 1%. That's pretty neat, right? So you're classifying only 1 in 100 the algorithm's getting wrong, which is, honestly, it's, considering the task, it's pretty amazing. Okay. So to further show that dropout does its job, what they've done is they've used multiple network architectures, so different kinds of architectures between 2 to 4 hidden layers and a different number of units, and showed that, okay, let me take a particular network architecture, let me plot the error rate as a function or as a graph with the number of updates or quote unquote number of iterations. And then let me just use that same network architecture, but also apply dropout and see what the curve looks like. And you can see that there's a very big gap here, especially as the number of iterations increases. This gap is pretty significant. This, without dropout, the error rate is around 1.75-ish, but with dropout, it drops to almost 1, right? Okay, so all of this is just to convince the reader that dropout actually works. It's an improvement. Okay, moving on. Let's talk about ImageNet. So like I said, ImageNet is nothing but a classified data set of natural images, right? This in particular is, so you have 1, 2, 3, and 4. Basically what this is it's the order and magnitude of the activations or the outputs of the output unit, right? So essentially, in this example, the neural network thought that this image was of a cheetah, and this is how much confidence it had, right? Then with very, with marginal confidence, it thought it was a leopard. And basically with no confidence, it thought it was a snow leopard or an Egyptian cat, right? So on and so forth for everything. So it essentially took the outputs and then sorted them based on what it believed the most likely class was for this image. And that's that's the table over here. The actual thing is whatever's in pink. So this is indeed a cheetah. This is a bullet train. This is a hand glass, and this is a moral. Now, as you can see, for the first two, it actually figured it out with pretty high accuracy, right? It really thinks it's a cheetah. It really thinks this is a bullet train. But over here, for the last two, it sort of wasn't really sure, right? That's fine. That happens. All we need is it to work in most cases, right? Okay. So like I said, the length of the horizontal bars is proportional to the confidence or the probability of how much it thinks that image is that particular thing. Okay. So what this is, by the way, this acronym, ILSVRC, it stands for ImageNet Large Scale Visual Recognition Challenge. So it's a competition. It happens every year. And they invite people and researchers to apply algorithms. And they submit an algorithm. And then they get tested. And the one with the lowest error rates or the best performance wins, right? So what the researchers did was they took the 2010 test set. It was the only one they had which was labeled correctly. And they experimented on it and figured out that if I were to take 5 convolution neural networks, it's just another modification, take the average and then apply dropout to it, I get the best performance. Okay? So what they did was they then actually submitted this dropout algorithm to the 2012 competition, and they won, right? Now, there's 2 columns here that matter. Top 1, this is basically how many times, what's the error rate of it getting the right class for the image as the first choice, right? And it failed 38.1% of the time, right? But it's still, its top choice was the correct classification around 62% of the times, right? But what's more interesting is that in most cases, with around 85%, the correct label for that image was in the top 5 choices of the neural network, right? I'm not gonna lie, I thought that was a mushroom. I did not know that was a moral. So it's doing better than me. At least it's, it sees the moral in the second chance. But yeah, so it won the competition. So it was, of course, the best over here. But if you look at the 2010 competition, it's doing better than everybody else as well. Okay. Something important to note is just using normal standard vision, you get something like 25.7, right? But with Dropout, you go down to almost 16%, right? So you get a very big delta, or a very big improvement, right? Which is staggering. Okay. We're going to have a small 5-minute break here. And then we'll continue with the salient features. And we'll just leave the rest for discussion. Okay? Cool. Any questions for this? No? Cool. Yes?
Can we eat donuts?
Yes, please. There's some donuts for you guys. Feel free to grab them. I don't know what we have got today. I don't know how to open this. Oh, it opens the other way. Feel free to grab some donuts. So, welcome back from the break. The salient features about Dropout are basically, they're trying to explore what Dropout actually does to a network, right? So if I given a network, if I if I pass a data set through it without Dropout, and then I pass a data set through it with a Dropout, what actually changes? What effect does this Dropout technique have on the weights and biases and on the output, right? So we're going to look at how it affects the quality of features, how it affects the sparsity of activations, more on this later, and how the performance changes when you change the probability of retainment, and when you change the network size, or when you change the amount of data you use. Okay, so like I said, they claimed earlier that Dropout works best compared to L2, L1, and max norm and some other ones. And you can see that here, right? Dropout is definitely one of the best regularization techniques. Okay, without further ado, let's go into the effect on features, right? In neural networks, the modifications you do in one unit depend on the activations or the values in the other units, right? So changes in one unit in a regular neural network might happen to fix up mistakes of some other units, right? So this unit is messing up, but all of these units that are connected to it are fixing it. These are the co-adaptations that we don't want, right? This is, going back to the gene analogy, these are genes learning to do like very specific things, right? We don't want this. So these unwanted co-adaptations cause overfitting. With Dropout, you can't rely on other units fixing your problem because those might not exist in a particular training set. So they never learned to rely on others, right? Okay, can someone guess what this image is? Someone who watched the 3 blue, 1 brown video.
Is it like the edges of the digit?
Yeah. So similar to the 3 blue, 1 brown video, what they did was they took each edge here, and they plotted it as a matrix, right? 724 by 724. And this is basically, dark means the weight is small, light means the weight is dark. But as you can see, for all of this, it's not really, it's pretty jumbled. It just looks like TV static to me. But after I apply dropout, look at what we get to see. I'm seeing dots, I'm seeing strokes, I'm seeing loops, curves, right, in different regions. So with dropout, it seems like each unit is actually learning something in particular. It's learning, this unit is handling just checking out whether or not there's a vertical line in the middle left portion of the image, right? And so on and so forth. This is good. This indicates progress. Okay? So each hidden unit over here doesn't seem to be detecting a meaningful feature, but with the dropout, you see it's detecting different sorts of features. It's detecting curves and lines in different parts of the image, right? Okay, cool. Effect on sparsity. Before we talk about that, let's see what a good neural network model should do. In a good neural network model, for a particular inputs, only a small subset of the units should have a high output, right? Like I mentioned, especially for the output layer, if the input was the handwritten digit 9, then I want the output for that output neuron or output unit to be high, and I want it to be low for everything else, right? Same thing internally as well. I only want a small subset of quote-unquote neurons to fire, right? I don't want everything to fire. So what that means is that small subset will have a high output or high activation, but the average activation across the entire neural network should be low, right? And we're going to see how that looks for this. So these two are for without dropout. This is for with dropout. I'll briefly talk about what activation and mean activation means. So activation, we talked about it, is just the output of a particular unit. High activation just means that the output is high, right? So what that means, it's strongly corresponding to the input data for that particular input data, right? So that if a unit's activation is high, that means that neuron is firing, it's active, right? It's playing a role in the network for this particular input. Mean activation is just the average activation across the entire data set for all of the 256 units that were used in this case, right? So all that means is this is the average of all 256 across the entire data set. And on average, you can see that the activation, you have a large, I don't want to say bimodal, but you have a large deviation from what should be the ideal case at 2, right? With dropout, we sort of see more of what we want, which is most activations not firing in general for any particular input, right? And some of them firing at a pretty high rate, right? So that's also a good sign that dropout is doing a good job. Okay. Next, we're going to talk about the effects of the dropout rate. So, like I mentioned before, P is the probability of retaining a particular unit. And this becomes a new parameter to tune, right? Neural networks have a bunch of parameters. One of them is the learning rate. But with dropout, this is a new hyperparameter. So they're testing a little bit of tweaking of P under 2 constraints. In one of them, they're keeping the number of hidden units constant. And in the other one, they're keeping the expected number of retained units afterwards constant. So we'll talk about what both of those mean. Okay. So keeping the number of units fixed, it just means I pick an architecture, and then if my probability of retainment is 0.1, I'm dropping 90% of the units on average, But keeping the expected value fixed means that, so for example, between 0.2 and 0.4, to account for P of n being fixed, this point, when it's 0.2, it has twice the number of units than the architecture when we're training with 0.4, right? In either case, what you get to see is, of course, on the training error, the training goes down as you increase the number of units, or you keep more units. But for the test, you sort of see this minima appear between 0.4 and 0.8, and over here at 0.6-ish, right? That's how they figured 0.5 is a good general value for P, right? Okay, so let's briefly talk about why we're getting a curve like this. Of course, at 0, if you're not keeping anything, your neural network is nothing. So your error is 100%. At 0.1, you still have a pretty high, all of that makes sense. But why does this go up again over here? Well, it's because at 1, it's just the normal neural network, which is overfitting. So it works amazing on the training data, right? You have an error rate of 0, but it doesn't work as well on the training, on the test data set, right? So you want your P to be somewhere in the middle, not so low that you don't have enough units to train, and not so high that overfitting comes back. Okay. There we go. The effect of data set size. It's pretty simple. More data, good. Okay? It's nothing like, it's not too much logic. There's nothing to think about here. More data, good, right? When your data set size increases, your classification error goes down. I'm not sure what they wanted to show with this, but they used a subset of the random handwritten digits. So I think they have 100, 500, 1,000, 5,000, 10,000, and 50,000. Also, pretty neat. This x-axis is actually logarithmic. Okay. So all of this is saying, more data good, but you can see these sort of two lines with dropout and without dropout intersect, and actually at the start, keeping all the units is better, right? But at some points, you have to consider the trade-off. So all they're saying is, if you want to figure out whether or not you should apply dropout, it depends on how much data you have, and you have to sort of figure out the right middle ground. Okay, sure. So we talked a lot about dropout. In conclusion, we saw that it reduces overfittings and improves generalizability. All that means is it does good on the test set, and it'll do good on any new input. And it does so by breaking up complex correlations that don't actually exist in the general sense. We also showed through experiments that it achieves state-of-the-art performance. One downfall of this is that it increases training time by a factor of 2 to 3. Why? Because for every unit, in every iteration, you have to do that random coin flip. And that sort of adds up, right? So another reason why the training time goes up is because you're dropping units at random. When you're sort of doing the backpropagation task of tweaking the weights to update the output so that it matches the expected output, you're not always doing so in the most optimal way. Why? Because you don't have half the nodes, right? So instead of finding the most optimal tweaks to get to a working solution, this is sort of suboptimal, and I like to call it stepping the steepest. In terms of gradient descents, it essentially means you're trying to find a minima. You're trying to minimize the error rates. and it's sort of like rolling a ball on a hill. Or you could extend it to 2D, 3D, whatever you like. But it's not, the ball will always go down the steepest path, right? But with Dropout, I guess the layout of the hills is sort of chunky. So it's not always going down the steepest path. It's sort of deviating a little bit. That's why the training time increases. So there's this sort of trade-off that you have to figure out, right? If you use Dropout, you're going to have to double the training time. But if you have that, I believe personally that you should do Dropout. Great. So that's it for the paper. It's an amazing paper, has almost 50,000 citations. There's nothing theoretically unsound about this. In fact, there's a lot of sections that I excluded in this because, like I mentioned, it goes into non-Bernoulli distributions. It goes into Boltzmann machines. It goes into pre-training. But it's a very interesting read. My critique of this is it could have been more beginner-friendly, right? Because the general concept of it was sort of muddled with all this complex terminology of like, posterior probability and Bayesian statistics and all of that, where in essence, it doesn't really mean too much for this paper, right? The introduction section of this paper was harder to interpret than the section that actually detailed how to do it, which I found funny. And section 7.2, by that I mean this section over here, this was pretty hard, especially interpreting these images. It was confusing for me. I had to go over it like 2 or 3 times to actually see what it meant. Other than that, good paper. Like me personally, I would accept it. Here's a neat little tidbit for you if you have the chance to see this. I'm not sure how I can open this. Once you guys have the link to the slides, you can check that. And essentially, you just have the link to the paper and the playlist over here. That's the resources. Please give both the paper a look and the neural network playlist a look. They're both really amazing. Okay. With that concludes the presentation side of this paper. We have about 15-ish minutes for discussion. So we're going to stay back and we're going to talk about this paper. But if you need to leave, you're free to do so. Of course, we were always free to do so. But thank you all for attending. And we do these paper reading groups every month, usually the last Friday of the month. It's not always about neural networks. It's not always, this just theoretical machine learning. Sometimes it's about some new data set that came out that is impactful. Could be about something other, some other machine learning technique. Could be very niche, could be very broad, right? Could be very recent. But yeah, if you like what you saw and heard here, please do join our Discord and all of this by scanning this QR code. And I hope to see you guys, of course, in the next paper reading group. With that, we're probably going to cut the recording, but then we'll proceed with the discussion of the paper. All right, cool.
I was just going to interject quickly.
Yes.
We pick these papers according to our knowledge of the sphere. But if there's ever anything that you want to cover specifically, feel free to reach out to us on any of these channels.
Is this the feedback form? Or
No,
is
this is our
this
lecture.
Are both of these the lecture?
Yeah.
This one? Yeah, this one.
This was, back in 2014, this was the bomb. And I had a really fun time